so last time I spoke about I'm more of an observer, I'm not a theorist particularly, so I talk about observational constraints on the standard cosmological model. And I talked about the CMB briefly and large-scale structure. So now I'm going to talk more about observational constraints on the standard model using a different set of observables, local astrophysical observables. And I'm going to explain how those introduce quite significant tensions, which suggest that the standard cosmological model might have some problems. And then I'll go further and ask whether the data supports the foundational assumptions upon which the standard cosmological model is based. Principally, is the universe isotropic, statistically isotropic? And then I'll close. So I was also going to talk about dark energy. So I produced many slides on that, but I've cut them down to talk about a restricted class of dark energy models, again, from more of an observational perspective. Because you'll hear a lot about scalar field, dark energy, and modified gravity in Professor Yamaguchi's talks. So I'll start with, I'll continue where I left off last time. So observations. So this is kind of like a 2-slide review of what I said before. Basically, yesterday you heard a few talks about the cosmic microwave backgrounds, and this is the latest data release from Planck, the Planck satellites. These points are measurements, and this blue line is the best fit from the standard cosmological model. And you have this very particular pattern, which Sokchon described very nicely in his yesterday in his talk. And this is due to the fact that you have this primordial hot baryon photon plasma, which is undergoing oscillations, and they are reflected in the power spectrum of the temperature fluctuations. And this is a tremendous success for the standard cosmological model. It fits the data very well. And so one thing I'll come back to later is there's an implicit assumption when you go from the cosmic microwave background temperature fluctuations to a power spectrum. You've made an assumption that you can decompose your ALMs into an angular power spectrum, and the Fourier modes are decoupled. And this is an assumption that the universe is statistically isotropic, and the temperature fluctuations are Gaussian. It means that all the information is contained just in these CLs. I'll come back to that later. So then I explained large-scale structure. So what we do is we take the primordial fluctuations from the temperature field and dark matter and baryons, and we propagate them forwards in time to the present time. And they are the seeds that create the structures that we observe today in the form of galaxy catalogs. And that topic is large-scale structure. And I argued that large-scale structure catalogs agree very well with...
Stephen?
Yes.
So in your previous, previous one, the independence of each mode, that's the you said assumption.
Yes.
So is it as a result of the homogeneity and isotropy, or so in other words, if we have some anisotropy, this assumption will be broken, or?
Yes, so it's the same in three-dimensional a space where you have a power spectrum in 3 dimensions, right? And then you make the assumption that if your density field is isotropic and homogeneous, then your power spectrum can only be a function of the absolute value of the Fourier mode. Okay, so that becomes an assumption, and that allows you to write your ensemble average just in terms of the absolute value of the Fourier mode, which in this case is just L. So this will be violated if your density field is statistically anisotropic.
Okay, thank you.
Okay, so like I said, the cosmic microwave background produces percent level constraints on the cosmological parameters. I'm going to come back to this later. So the Hubble parameter today, the expansion rate of the universe today, as predicted by the CMB, is 67 plus minus a half kilometers per second per megaparsec. So this will be relevant later. It's a very tight constraint on how fast the expansion rate, how fast the universe is expanding today, but it's subject to assumptions, model assumptions, that we assume that the lambda CDM model, the standard cosmological model, is correct at all times. So then I tried to argue that if you take a look at the large-scale structure catalogs, you find that they are in very close agreement with the CMB. And unfortunately, I used this plot, which Sokchon correctly pointed out is from a long time ago. This is from 2004. This is slightly lazy on my part. And this data has been kind of massaged to, so these are different redshifts, different biases, and there are different epochs where different physics is at play. So this is a slightly misleading plot. So I just want to correct that slightly now and just show you the most up-to-date large-scale structure results. So this was published in 2020 by the BOSS team. So BOSS is a cosmological scale galaxy catalog that has luminous red galaxies over a wide redshift range. This is the largest publicly available galaxy catalog currently available. There will be future larger scale catalogs, but this is the largest that we currently have. And the BOSS galaxies go from roughly redshift 0.1 to around 0.6, 0.7. And there's around of order of hundreds of thousands of galaxies over a gigaparsec volume. So it's very large scale. And from the galaxies, you can measure the power spectrum. So this is the galaxy power spectrum of the BOSS galaxies. Now, the power spectrum of the galaxies is anisotropic because of redshift space distortion, which means you have to decompose it into angular modes, L equals 0 and L equals 2. So we have a monopole and a dipole. And these points here are measurements of the power spectrum in the late universe for two different galaxy samples. So there's a high redshift one and a low redshift one. And from this, the shape of the power spectrum, you can constrain the cosmological parameters. And these are the most up-to-date constraints from large-scale structure. So this is the baseline model. If you fix NS in the blue and gray is if you allow NS, the primordial scalar, spectral tilts of the power spectrum to vary, which you should do. So the red curves here, the red constraints are from Planck, and let's say the gray constraints are from the BOSS data, and you see that it can constrain the slope. The galaxy data can constrain the slope of the primordial power spectrum, the amplitude of the matter power spectrum, which is sigma 8, the total matter fraction omega m, and the Hubble expansion rate h0. And you can see the marginalized one-dimensional contours here, one-dimensional PDFs, probability distributions of these parameters. And they agree perfectly with Planck, so almost completely. So the only slight tension is in sigma 8, which is the amplitude of the power spectrum, which you could say is slightly low. So the best fit from the BOSS data is marginally low relative to the Planck best fit. But this tension is only something like 2 sigma, maybe even less than 2 sigma. So it's not very significant.
About the graph you showed here, so the right-hand side, two plots. So those are more or less at the fixed distance from us. Is that right? Or fixed time in the evolution of the universe in a sense, because the Z effective is a fixed number, right?
Yeah, so Z effective is kind of like the average redshift. So what they do is they measure galaxies over a redshift range, and that redshift range so there's two different samples in BOSS. There's the low Z, which is a set of galaxies that runs from around 0.1 in redshift to 0.4, and this is the average redshift of that galaxy sample.
So, but the spread along the Z, that's also very wide range. My question is whether it is actually two-dimensional data or three-dimensional data.
It's three-dimensional data. So Z effective here is just used as a guide, just to say that this is the kind of the mean redshift, or the if you account for the volume effect. Now that is a good question in the sense that the amplitude of the power spectrum is a function of time. But what you do is you measure sigma 8, which is the redshift 0 amplitude of the power spectrum, or AS, which is the primordial amplitude of the power spectrum, and then the actual power spectrum that you measure, you shift to the effective redshift of the survey. So there is some, you could argue that actually the power spectrum is evolving from redshift 0.4 to 0.6. So this line, you can imagine, would shift slightly over the range of the galaxy sample which you're sampling, but that effect will be very small, and practically, in terms of the amplitude at least, and the shape, it's fixed over the range that they're looking at.
So the evolution of the power spectrum, what is the origin of the evolution? Because of the all the metals and radiation contents, time dependency is different because of that, or?
So the power spectrum evolves so in many ways. So it evolves in amplitude, because that's just large scale clustering. Everything's just falling into overdensities. Okay, so things are getting more dense over time. So there's an increased clustering as a function of time. Then the small scale, the actual shape of the power spectrum evolves because gravity is nonlinear force. So there's a mode coupling between these Fourier modes, and there's more power generated on small scales. Because power is kind of propagated through these modes. So you get more power on small scales, and so you find a tilt in this power spectrum. And also the properties of the galaxies that you measure vary from high redshift to low redshift, and you select a subset of galaxies. You don't select all galaxies. So your actual, the relative amplitude of this power spectrum can increase as a function of time if you measure what you think are the same set of galaxies at low redshift and high redshift. They would have a different amplitude because you're effectively measuring different subsets of galaxies. So there's lots of reasons why this line here, this figure, will evolve. But over the redshift range of the survey, which is like plus minus 0.1, plus minus 0.2 maybe, practically, there's no significant evolution.
So can we say that there's a peak in the curve, right? And which is between 0.05 and 0.1. So that may be the the 20 megaparsec or something. So it's like the supercluster scale is dominating. Can you say it that way, or?
No, so this power spectrum is the same as the matter power spectrum. It's just been multiplied by K. The Fourier mode.
I see.
So it's actually the power this power spectrum, but it's just been multiplied by K. So the physics is the same. So large scale structure just growing on subhorizon scales, and then this is the suppression of power. Now, so this is actually very large scale. So this is the corresponding scale in megaparsec associated with the Fourier mode. So you're talking about hundreds of megaparsecs at the turnover.
And the question is, this graph, this is, the before decoupling, right? Due to the coupling with the radiation is damping or suppression, that kind of things. Yes, but after decoupling, as you said, that due to the nonlinearity of the gravity and the etc., so still the power spectrum will evolve. That's what you're saying.
So this is the power spectrum after decoupling. So this is the late universe matter power spectrum. Okay, so
after decoupling.
So this is what you would observe if you look at any large scale structure catalog from redshift 0 to redshift 10, and you'll never go beyond 10 practically. This is the power spectrum that you would measure. So you're looking at subhorizon modes predominantly, which are like here. So the very largest scales we're not going to measure very effectively because the volume's not there. So we in terms of large scale structure, you're interested in small scale modes that have all across the horizon, from sort of like of order of a gigaparsec scale to 1 megaparsec scale. Contains practically all of the cosmology, and in that regime you're just looking at subhorizon physics and practically Newtonian physics.
I see. So even though this is the dark matter, so this will not change as a function of time.
It will change as a function of time, but so if you look at linear perturbation theory, all that will happen is the amplitude of this power spectrum will increase during time as a function of time.
Okay.
If you look at the nonlinear physics, the shape changes as a function of time. So at very early redshifts, you'll have this blue curve. This is the linear matter power spectrum. But then as you evolve your density field, due to these nonlinearities, you pick up excess power on small scales.
Okay. Okay. Now I understood. Thank you.
Okay. Yeah. So anyway, so the point I'd like to make is that all of the cosmological parameters that you can measure from the latest, most up-to-date large-scale structure catalogs are practically consistent. The constraints are weaker than Planck because Planck is the kind of the best data set we currently have. The next generation of galaxy catalogs will improve over Planck, but at the moment they show consistency.
One more thing is, then can we, what can we say by comparing the two in the right-hand side? The one is 0.61 is further away, is the early time, and then the bottom one is 0.38, somewhat a more recent time. So the what can we say about the little bit different spectrum? Can you say something?
So if you measure, you can to an extent. It's difficult because
it's not that big different time.
Yeah. So first of all, it's not that different a time. But the second, there's a big problem with galaxy catalogs at high. This is considered high redshift for observations of galaxies, right? And so these galaxies, you have to select a subset of galaxies. You can't just find all galaxies above a certain brightness at these redshifts because there's too many. So you can't get accurate spectra for 1 billion redshifts, or we can't at the moment. So you have to select galaxies based on certain properties, like the color of the galaxy, and these are selected differently. So because these have to be brighter galaxies, basically, as you go to higher redshift, you have to find the brightest galaxies. So there's a selection effect which also goes into the power spectrum.
Okay, I see. Okay.
Yeah. But you can. The answer is you can, though. You could measure the relative amplitude shift, and there will be a growth in this, but there will also be a change in the bias, is what I'm trying to say, the galaxy bias.
Okay.
So the other thing I'd just like to say is we can, from the galaxy catalogs, we previously talked, and Sokchon talked about the galaxy power spectrum, and it's a function of the dark matter power spectrum and this thing called a galaxy bias, which is fixed, and there's a degeneracy between the amplitude of the dark matter power spectrum and which is sigma 8 and the galaxy bias, but galaxy bias is something that's very well understood, and we've measured it. So this is the state of the art in current galaxy catalog and power spectrum measurements, and this is the galaxy power spectrum, and is now known is a solved problem up to third order in perturbation theory. So this assumes linear perturbation theory. Obviously, that's not valid on smaller scales at late times because gravity is a nonlinear force. So you have to go to higher order perturbation theory to understand the galaxy power spectrum. And you end up with a very large, this is not my work, this is Vonimir Vlas's work, but you end up with a very complicated power spectrum, which is given by a sum of higher order terms. So these are convolutions of the squares of the power spectrum. And these are the linear combinations that you get if you just do linear theory. But now you have all of these additional terms, and these additional terms affect the shape of the power spectrum on small scales. And so by measuring the shape of the power spectrum, you can actually break the degeneracy between B and sigma 8. So here there's an exact degeneracy, but you see that B1, the bias, enters at different orders in this perturbation expansion. So if you do the full perturbation theory, you can break the degeneracy between the galaxy bias and the amplitude of the power spectrum, and you get a constraint on the primordial amplitude of the power spectrum. And that's how you do that for large-scale structure. Okay, so that was a review of what I talked about yesterday. So now let's go on to the next cosmological observations. It's completely different, and talk about type 1a supernova. So type 1a supernova are white dwarfs. They exist in our local galaxy in the Milky Way and also in many other galaxies. And they exist, they're white dwarfs that exist in a binary system. So we haven't measured this. This is just a model on how we think these things form. So you have a relatively low mass white dwarf, and it accretes matter from its companion, and it gains matter gravitationally. And then eventually its mass passes a certain limit, the Chandrasekhar limit. And once the mass becomes sufficiently large, the star can no longer support itself through its pressure, and it undergoes catastrophic collapse. And that collapse heats the contents of this white dwarf, initiates carbon fusion, and this is a runaway explosion that creates a tremendous amount of energy. So it's a very quick process. It happens over a time scale of order 40 or tens of days, let's say. And during that epoch, these white dwarfs, which go supernova, are extremely bright. So they're of order of 1 billion times brighter than the sun as we measure it. And they can outshine, during the time in which they're undergoing this thermonuclear explosion, they can outshine, they'd be brighter than the galaxy in which they are contained in. So that's good, because cosmology, we like bright objects, makes them easy to observe. And so we can measure them, measure their brightness, and we can measure their brightness as a function of time and get their light curves. And the reason why supernova are so useful for cosmology is because the actual physics, the physical processes that cause these supernova to collapse and then initiate carbon fusion are very well understood. Okay, so it doesn't matter where these things are in the universe. You know, once this white dwarf has accreted sufficient matter that just passes a certain limit, it will undergo this collapse and this fusion process. And gravitational collapse locally is very well understood. Fusion is very well understood. Stellar physics is very well understood. And so no matter where they are in the universe, these events will always happen via the same physical process. So we expect them always to have practically the same absolute magnitude. They will emit the same amount of radiation, regardless of where they are in the universe, either in our Milky Way or very high redshift galaxies. So that means what are known as standard candles. A standard candle is something which has the same absolute magnitude, regardless of where it occurs in the universe. So the absolute magnitude of these objects is fixed. Now, that's very good, but it doesn't completely help us for cosmology, and the reason is as follows. So what we actually measure in cosmology is not the absolute brightness of an object, the absolute magnitude of an object, sorry. We measure its apparent magnitude, okay, the brightness or the magnitude of this object a certain distance away. So this is the brightness that we would measure on Earth of a distant object. This is the absolute magnitude, which is generally something we don't know for any given process. We know it's constant, or we think it's the same for all supernova, but we don't know what this value actually is. And the difference between the magnitude that we observe and the absolute magnitude is called the distance modulus mu, and it's related directly to the distance between us and that object via this relation. So this is just log 10 of the luminosity distance, which is sensitive to cosmological parameters, omega matter and omega lambda. And it's also sensitive to h naught, the expansion rate of the universe today, which practically normalizes distances. Okay. And so we measure m, but we can't measure h naught directly from this equation here, because we don't know what m, the absolute magnitude is. And you see that there's a perfect degeneracy between how bright something is and how far away it is, which is a distance which is scaled by h naught. So there's this degeneracy, which means even if we measure the supernova, we can't measure h naught directly, just from the supernova. But we can measure, if we just treat this m and h naught as just nuisance parameters, they're just kind of like 0 points in a redshift dependent curve. You can constrain omega matter and omega lambda just by measuring the redshift dependence of this distance modulus. And that's what was done in the early supernova papers. So this is the original results where supernova were first used in cosmology by Rees et al. Also Perlmutter in 1998. So this is the work that won the Nobel Prize. They found that the supernova favored a value of the cosmological constant that is non-zero. This is the constraints they derived on their original supernova samples on omega lambda and omega m. And to do this test, they didn't care what H0 was. In fact, they fixed H0 and then they just fit the supernova light curves to find m given that H0. And they didn't care. So this is the distance modulus as a function of redshift. And you can imagine that this combination of H0 and m just shifts the curve in the y direction. But if you just fix the 0 point of this curve and just look at the shape, the redshift dependence of the distance modulus, that gives you a constraint on omega m and omega lambda through this luminosity distance. And that's what they did, and they found that lambda is non-zero to pretty high statistical significance. If the universe is flat, then you're on this curve here, and then this is the best fit values of omega lambda and omega m, a number of sigma away from zero. But we want to do better, so we can constrain omega m and omega lambda with the supernova, but we want to be able to measure H0, okay? And so to do that, we have to break this degeneracy, and that means that we need to try and find a way of estimating the absolute magnitude m of a supernova.
Oh, Stephen, so roughly, so if we increase H0 or decrease, roughly how will it change qualitatively the most probable values?
In here it won't at all, because what they do, so what the supernova team did is they fixed H0, okay, and then so what you have when you have supernova, what you measure when you measure supernova is kind of like the brightness of that supernova as a function of time over its while it's exploding, right? So you over the course of like 40 days, you have a peak. Okay, it looks like a peak brightness, and then it just tails off. And those are standard counts. So each supernova has its own light curve, and they can be standardized, and you fit a certain set of parameters. And one of those parameters is the absolute magnitude of the supernova, okay, which is a free parameter in this fit. So what they do is they just find this, given a H0, they find the absolute magnitude of the supernova as a fit to the light curves. And then from that, they just use this combination here, and they just they vary the parameters, omega m and omega lambda, to find the best fit parameters. Now, if they changed H0, what would happen is their absolute magnitude, when they go to fit at the supernova light curves, when they fit m, that would change in such a way that you would get the same answer for omega m and omega lambda.
Oh, I see. So the most probable, the omega m and omega lambda eventually may not depend on H0.
So if you just measure the redshift dependence of this curve, and you if you just combine this log 10 H0 and m together as a single parameter, then you can then you just fit it as a parameter.
I see. Okay, thank you.
Okay, so that was the status of supernova data in 1998, and as I said, this won the Nobel Prize for proving that dark energy in the late universe is present.
But usually supernova prefers some special value of H0, like a 70 something.
Yeah, so that was I'll explain now how. So if
I'll wait then. Okay.
Yeah, okay. So this measurement is just assuming that we have supernova. Okay, so if we only have supernova, then what I'm saying is we can't determine H0. That's true. But if we know what m is, if we know the absolute magnitude of the supernova, then we can, because then we can just fit the zero crossing of this curve practically, and we measure, and then we can measure H0 directly. But to do that, we need the absolute magnitude.
Okay, I understand.
So that is what people did subsequently, using a very clever method, in my opinion. So to measure H0, we need m, the absolute magnitude of the supernova. To estimate m, what they do is they create what's called a distance ladder. And a distance ladder is a series of astrophysical measurements of different objects. And each step in that ladder, they calibrate a standard candle in such a way that initially you get a distance to a certain object, and then you use that object's properties, like its magnitude, to then calibrate another distance at a higher redshift. And then you use that distance to calibrate the highest redshift sample. So it's a ladder in the sense that each rung in that ladder, you use an astrophysical object, an astrophysical measurement to calibrate a property of these astrophysical measurements. And that's what they did. So they periodically, they took a low redshift sample of objects, and then they used them to calibrate the absolute magnitude of the supernova. And I'm going to show you the steps they did to do that briefly. Okay, so they used, so the only way, or I'd say one of the only ways of getting a true measurement of distance at astrophysical scales, at very large scales, is to measure parallax. So I'll explain what parallax is in a second. And they used parallax to measure the periodicity of Cepheid variables. So I'll explain what Cepheid variables are as well. And then they found Cepheid variables at higher redshift and used them to calibrate the absolute magnitude of supernova. So it's kind of a series of steps, which I'm now going to describe. So first of all, you need to know what parallax is. So parallax is a very old method of measuring distances. You can do it yourself if you just put your finger in front of your eye and blink one eye and then the other eye. You see that your finger moves relative to the background, and that's exactly what you measure when you measure parallax. So if you have we're on the Earth, we're orbiting the sun, and you point your telescope in the direction of a series of local objects such as stars, and you measure the position of these stars relative to background objects. Okay, so background objects are a very long way away from us, will not move as we observe them in the sky. Well, they'll move a very small amount, but practically very distant objects won't move as we observe them at different points in our evolution of the sun, rotation around the sun. But small objects close to us will move, okay? And that's just because relative to the backgrounds, okay? So that's what parallax is. So if you measure the position on the sky of a series of stars when you're at a certain point in our rotation around the sun, and then 6 months later you point the telescope at the same stars, you'll see that they will have moved very slightly relative to the backgrounds. And from that you can deduce the angle that they've moved from as the Earth has moved around the sun, and you know what the distance is between the two measurements. Okay, it's just that this is 1 astronomical unit. So this triangle here has a base of 2 astronomical units. And so if you know an angle of a triangle and you know the base of the triangle, then you can estimate this distance here. So that's all parallax is just angle variations in the sky as we're moving relative to a set of background objects. So that is a method by which we can construct a distance. And it's one of the few methods that's actually known. And so what you do is you can measure the distance to certain stars using this method. Now there's a certain type of star called a Cepheid variable star, which are very useful for cosmology. And what they are is they're pulsating stars. Okay, so they're made of hydrogen, helium, and some heavier elements. And why they're interesting is they have an inner core and an outer envelope, and that outer envelope periodically expands and contracts. And it does that because of its particular chemical composition. It's a particular kind of helium, and as the central core is emitting radiation, and when the outer envelope is very dense, when the star is very small, it absorbs all of those photons, and so the outer envelope gets hotter, and as it gets hotter, it expands because it has radiation pressure. As it expands, the star becomes transparent, more transparent to radiation, and so it starts to cool. And then gravity takes over, and gravity pulls the envelope back towards the center. And so you have this periodic fluctuation in these Cepheid variable stars. And the magnitude of these stars is directly proportional to the period, or is related to the period, log of the period of its rotation, of its pulsation. And so these are actual measurements of Cepheid variable stars at different wavelengths. So you measure the frequency of the photons, you measure them at different wavelengths, and you see this linear relationship between the magnitude and the log of the period of this pulsation. And this is, again, a standard candle. This is a standard process because regardless of where you are in the universe, this is very local physics, okay? You're just talking about a star which is emitting radiation and under well-known physical processes. It's just gravity and photon absorption of a particular element. So you'd expect these curves to be the same, regardless of where this Cepheid is. But again, with Cepheid stars, we have the same problem. We can't measure the absolute brightness of a Cepheid variable. We can only measure its apparent brightness because it exists a certain distance away from us. But what we can do is, if we have Cepheid variables very close to us, then we can measure this angle here due to parallax, and we can measure the actual distance between us and the Cepheid variable stars. That allows us to calculate exactly the magnitude, the absolute magnitude of the Cepheid variables. And that allows us to fix, in an absolute sense, this relationship between the absolute magnitude and the period of this pulsation. Okay, so that is the lowest rung of this distance ladder. So what they do is they use the Milky Way Cepheid variables, and because we measure the apparent magnitude of these objects, and because we know the distance, we can measure the absolute magnitude. Okay. And then, so this is the first step of this distance ladder. These are for local Cepheid variable stars in our Milky Way, but you can also measure them in very nearby galaxies. And then what you do is you take these objects and you look at higher redshift. So this is a set of galaxies, a redshift around 0.01, so it's still very local to us. And you look for galaxies that contain both Cepheid variable stars and type 1a supernova. And there's an order of 50 of these that we've found so far. There's not many. It's very difficult to find supernova Cepheids because we need to find them at very low redshifts because we need to be able to measure the periodicity of these Cepheid variables. So why this is interesting is because we've inferred the absolute magnitude of Cepheid variable stars, and when at higher redshifts, we can't measure parallax at these high redshifts because the angle differences that you measure are too small, so you can't resolve them. But what you can do is measure the apparent magnitude of the Cepheid variables, and you can measure the periodicity of their pulsation. And because we know the absolute magnitude of these objects, we can infer from this, we can measure the distance to these objects. Okay, so now we have a set of galaxies which through the Cepheid calibration, we know the distance to them. Okay, and that means that in terms of the supernova, we can measure the absolute brightness of these objects. So now for this particular subset of supernova, we know the apparent magnitude, we know the absolute magnitude. Okay, so because we know the distance. Okay, so we don't need to worry about H0 because we just measure the distance, or we infer the distance from the Cepheid variables. And now we're done, okay, because the assumption is that the supernova are standard candles, okay? So we've measured the absolute magnitude of these supernova. There's only around 50 of them, so they're no good for cosmology. But now we look at the high redshift sample of supernova, which are over a redshift range of 0.1, let's say, or 0.005, all the way up to a redshift of 2. And now we measure the apparent magnitude of these supernova. We've inferred the absolute magnitude of this supernova from this distance ladder. So we can measure the redshift evolution, which gives us omega m and omega lambda, and we can also now directly measure H0 from these supernova. So this is called the cosmic distance ladder, and it gives us a constraint on H0. Okay, so and this is the results of doing that. So this is the supernova. This is the SHOES team led by Reese. And this is the measurement they get. This is 74 kilometers per second per megaparsec plus or minus 1. So it's a 2% measurement of H0 inferred from the distance ladder, or is now reduced so approximately 1%. It's between 1 and 2%. Now, the problem with this is if you compare this to the measurements that you obtain from the lambda CDM model from Planck, this is the best fit Planck results, okay? So this is the, if you take the cosmic microwave background and assume that the standard cosmological model is correct, all the way from recombination to the present, this is the value of the Hubble constant that you infer from the standard cosmological model from the early physics. And in fact, even if you don't look at Planck, if you want to look at alternative data sets in the high redshift universe, you find consistency with Planck. You find that this parameter is around 67 plus minus 1. Now, this discrepancy is something like 5 sigma, so there's 5 standard deviations between these two measurements now, which suggests that there is some fundamental problem either with this data set, or there's a third interpretation which suggests, which could be that because these measurements depend heavily on the cosmological model, it could be that the standard cosmological model requires modification. And it could just be that we've assumed an incorrect model when in our measurements of the Planck data. So obviously these measurements have been repeated by lots of different groups now. So they can be broadly split into sort of cosmological model dependent results, which are here, which is the cosmic microwave background, Big Bang nucleosynthesis, and also BAO should be here as well. That's no CMB with BBN. And then you can also, so the distance ladder that I described in the previous slide assumes or uses Cepheid variables, but really any astrophysical event which is independent of cosmology, independent of where that occurs in the universe, can be used. So for example, you can use the fact that when stars exceed a certain mass or a certain chemical composition, they will undergo helium fusion. Okay, so this is what's called the helium flash, and that occurs at a very well-known mass scale. And again, the physical processes of helium fusion are very well known, so we can use that as a standard candle. So anything that we can measure that's independent of cosmology, that's astrophysical in nature, we can in principle use as a standard candle. And if you use various different standard candles, you find and use them to calibrate type 1a supernova, you find all these different measurements here, which I'm not going to go into them. But what's interesting is all of them, every single standard candle that's been used, there are various best fits and there are various statistical uncertainties. Some of them are very poor methodologies, or they don't have statistical power. Some of them are very good, so the tip of the red giant branch is typically considered very good, and the Cepheids. But the point is that all of these predict a higher value of H0 relative to the cosmological expectation value from the CMB. And if this, if this discrepancy, this 5 sigma discrepancy, was due to some systematic effect in the data, so something that we just don't understand, or just some measurement error in the astrophysical measurements, we would expect there to be fluctuations on either side of this the cosmological best fit, because each of these measurements has a different set of systematic uncertainties, and they wouldn't be correlated. Okay, so there's no reason why all of these points have to be on the right-hand side of the best fit value of H0 from the cosmic microwave background. So it suggests that this measurement is robust, and this measurement is robust. And so it could suggest that there is new physics to be found in the cosmic microwave. In the standard cosmological model, might require some modification, and that is the origin of this discrepancy. Now, the Hubble tension is a very controversial subject, so lots of people have got an opinion on it. So the Planck team will have said to me before that if you disagree with the cosmic microwave background, you're just wrong about something. The Hubble, these guys who measured the Hubble tension, who measured the Hubble parameter using Cepheid variables, think that this is a 5 sigma result, and they're very confident of their result. And then there are other people who just don't believe that the standard cosmological model is valid over all of the scales and all of the redshifts used in these analyses. So they say that it's either not a well-defined problem, and there's some people who are very blunt about it. But anyway, you should also consider that this is a century-old problem. So people have been trying to measure the expansion rate of the universe since the 1930s and even before. And this is a plot of a measurement of H noughts, so measurements of the Hubble parameter as a function of the year in which they were made. And the early measurements of the Hubble parameter, when cosmology was really a new subject, were of order of 500 kilometers per second per megaparsec. And interestingly, the original papers that were measuring the Hubble constant were using Cepheid variable stars. Okay, so this is in principle the same data as used down here. You see this huge discrepancy in the measurements, and this is because back then telescopes weren't of sufficient resolution to be able to resolve single Cepheid variable stars. So they're actually measuring groups of stars and mistaking them for a single star. But it's an interesting point to note that their error bars are actually very small, and that's because these are subject to systematic effects that at the time they just didn't know and didn't understand. So it's entirely possible that there is some unknown systematic that's still affecting our data. Now that's there's obviously been a lot of work done on systematics, and the results are very robust, but there could still be some systematic in the data. But also there's also historically been a Hubble tension, so you can't really see it here, but in the 1970s through to the 90s, there was two different groups measuring the Hubble constant, and there was a group that found that it was 100, and they were very adamant that it was 100, and then there's another group which were very adamant that it was 50, and that's led to a very bitter argument in the astrophysical community, and it led to the formation of a project with an express design to measure the Hubble constant to 1%, and the end result was the measurement is around 70, so somewhere in between the two measurements. So this is the emergence of tension. So at very late times, you see these are the Planck measurements. So this is the cosmic microwave background measurements from WMAP, the previous telescope that measured the cosmic microwave background temperature, and these are the Planck data results, and these are the results from the later Cepheid variables. And you see that this tension is newly re-emerged. There was agreement between the two methods, but as the data is improved, you find this this discrepancy. So I'd like to stress that cosmology is not the search for one number. It's not the search for two numbers like it used to be called. So there's actually a wide range of cosmological parameters, and the Hubble tension is just one. And still, the cosmological model, the standard cosmological model, seems to work very well apart from this discrepancy. There are a few other mild discrepancies that are now appearing as data gets better. So I've just shown a couple here. So there's this sigma-8 tension, which, as I've said, the large-scale structure of the universe seems to prefer a slightly lower value of sigma-8 in combination with omega m. So this is the data. This is the best fits of these cosmological parameters from weak lensing data here. And this is the Planck. So Planck is obviously much tighter constraint because it's a very good data set. It's the best data set we currently have. And there's this slight tension whereby the large scale structure slightly favors a different cosmological parameters. But this is only very weak tension. And I don't think this is a very serious problem for now. It may get worse over time as large scale structure data sets improve. There's also the A lens tension. The A lens is a phenomenological parameter that's added to the cosmic microwave background because so the cosmic microwave background photons are actually lensed. So as they pass from the surface of the last scattering to the present time, the photon geodesics are slightly perturbed by the large scale structure in between us and the light scattering surface. So that slightly creates a pattern in the cosmic microwave background temperature fluctuations. And the effect is to wash out structure in the power spectrum. And the Planck team added this constant factor, which should be unity if the standard model is correct. So if we understand this effect due to lensing on the power spectrum, this parameter should be unity. And this black one here is the measurement, the best measurement we currently have of this parameter A lens, and it's discrepant, it's high relative to its expectation value by a few sigma again, so maybe 2 and 3 sigma. Again, this is a very weak tension, but it is present. So the point I'm trying to make is, in the past, the cosmological models seem to work very well. and it still does work pretty well. But they're increasing as the data is getting better. We're finding holes in the data and problems and tensions. And the most serious one is without a doubt H0. Okay, so can I have, okay, so let's say I've got 10 more minutes. Is that okay?
Yes, okay.
Okay, so 10 minutes. So I'm just going to talk about the standard model in another context now, and the observations of isotropy. Okay, so so going back to the beginning, so one of the foundational assumptions of the standard cosmological model is that the universe is statistically isotropic on large scales. Going back to the matter distribution, if you're an observer and you look at your matter distribution and you point your telescope in a direction of the sky and you measure the power spectrum or any statistical property of this distribution, and then you point in a different direction of the sky, you should find statistically that your results are consistent. That's isotropy, an independence of physical properties on direction. And that's been very well tested in the cosmic microwave background. So if you actually look on the sky and measure the photon temperature from the cosmic microwave background, you find that it's an almost perfect monopole on the sky, so of temperature 2.725. So this is the most perfect black body that we know. Certainly in terms of, well, so in cosmology, it's just astonishing that it's isotropic. The universe is almost perfectly isotropic. The surface, and what that means is that the surface of last scattering relative to us, if we're in the center of our light cone, the surface of last scattering is an almost perfect sphere around us, and the photons are all traveling along geodesics, and the geodesics, there's a spherical symmetry implicit, which it should be if the standard cosmological model is correct. Now, if you subtract the monopole, so if you just subtract this temperature from every pixel in the sky, this is what you observe. So this is our galaxy. This is just noise, this line here. And you see what, again, looks like an almost perfect dipole. And this dipole has an amplitude of 1 pi 10 to the 3. And the dipole is due to the fact, or this in the standard model, we assume that this dipole is due to the fact that we're moving. Okay, the Milky Way is undergoing peculiar motion. It's falling into a larger gravitational potential well, and so we're moving with respect to the cosmic microwave background photons. And so you can imagine if this relative motion will produce a Doppler shift in the photon. The frequencies will be slightly blue shifted in one direction relative to the other, and that will create this dipole in the temperature. And so if you subtract that, then you find the temperature fluctuations that are at 1 pi 10 to the 5 relative to the monopole. And then we assume that these are primordial, and these fluctuations here are drawn from a Gaussian random field that is statistically isotropic and homogeneous too. Okay, so that's the assumption. Now, the fact that we measure a dipole relative to the cosmic microwave background means that we should also measure a dipole relative to large-scale structure. Okay, and the reason for that is if you look at galaxies or any object like quasars, a very large distance from us, those objects should be at rest. They should relative to the cosmic microwave background. Okay, so the universe on large scales has no bulk flow. There's no net velocity between different components, like between the radiation and between the dark matter on very large scales. Okay, so what that means is the galaxies and the quasars and the large scale structure at large scales should be stationary with respect to the CMB. But what we measure when we measure a galaxy catalog is a set of objects below a certain threshold limit. So we measure all objects brighter than a certain magnitude. Okay, and you can imagine that if we're moving relative to large scale structure, the frequency that we detect for any particular object like a quasar will be slightly redshifted and blue shifted depending on our motion relative to it. Okay, and so that will mean that if we measure over the entire sky, if we measure a distribution of objects and we basically count objects in the sky that are above a certain flux limit. Okay, so a certain number of photons above a certain flux, and we count all these objects because the objects that we measure typically have a energy distribution that is a function of their frequency, which is nu. And because this frequency is going to vary on the sky because we're moving relative to these objects, that if we select all objects greater than a certain flux, because the flux is now a function not only of frequency, but of our velocity relative to that object, we will measure a dipole in the sky in objects selected using the flux limit. And that number density fluctuation relative to the monopole, the average over the whole sky, is going to be related to the energy distribution through alpha, the flux distribution given by this parameter x. These are can both be measured. Our velocity, the frequency of the observation, and the angle, the relative angle between the observation and the dipole direction. Okay, and that gives us a dipole in the number counts. Okay, and the dipole in the number counts is just given by this. So these are parameters we measure, and this now is the velocity. Sorry, I use velocity interchangeably here. So this is the velocity, this is the frequency. This is just a nomenclature error. So anyway, so if we measure a distribution of objects in the sky based on a flux limit, we should measure a dipole in that number count, and that is directly related to our velocity relative to this distribution of objects. And so this was done. So this has been done many times. So the mathematics of this dipole has been known since 1984. People typically measure radio sources for this because radio sources have certain properties which are very favorable to this measurement. They're not prone to dust extinction, and they're easy to detect because they're typically bright. So we use quasars, so you can detect them at high redshift. And this was done most recently by CQUeST et al. In 2021. So it's a very recent measurement. So they looked at high redshift quasars. So this is the distribution of the data that they have. So it's very high redshift relative to large scale structure. And then this is the number density of objects of quasars on the sky. This is in galactic coordinates. So the galaxy is here, and the galaxy is cut from the sample because it could interfere with measurements. So we make a galactic cut. And then if you just smooth this distribution of points using some smoothing scale and subtract the monopole, this is what you observe. And you very clearly see a dipole in the number counts of these quasars in the sky. And that's good. That's exactly what you should see, because according to the standard cosmological model, we're moving with respect to the cosmic microwave background. So we should also be moving with respect to the quasar distribution, the matter distribution at high redshift. But the problem is that the dipole that we observe in the galaxy catalogs is very, very high relative to the cosmic microwave background. So this is the probability distribution of the dipole, and this is the dipole that we measure. So if you assume that, so if we know the velocity of our motion with respect to the cosmic microwave background, you can get the dipole that you expect from these catalogs. And this is the expectation value you would get if we were moving with the velocity of the we're moving with the velocity that we are with respect to the CMB, also with respect to the quasars. And this is the distribution that we expect. This is the statistical uncertainty we would expect due to fluctuations in the velocity. But this is what's actually measured. And this is the direction of of our motion with respect to the quasars, the large-scale structure, and this is the cosmic microwave background dipole. And again, so what you see is a statistically significant discrepancy between the cosmic microwave background velocity, our motion with respect to the cosmic microwave background, and our velocity with respect to the quasars. And what that suggests, if this is an accurate measurement, is that the quasars can't be at rest. The distant large-scale structure can't be at rest with respect to the cosmic microwave background. They must be in relative motion to each other because they are both in relative motion to us with different velocities. And the claim by this group now is that this is a 5 sigma detection of a relative velocity between the CMB and the large-scale structure. If that's true, it means that the universe can't be statistically isotropic. Okay, there has to be a bulk motion on cosmological scales. So now we can just go back quickly and look at the cosmic microwave background and say, well, is the cosmic microwave background actually isotropic? And remember that we've assumed that it is because we've written this down. We've said that it's a statistically isotropic Gaussian random field. and all information is contained in the power spectrum. If you assume that, then you get good constraints on cosmological parameters, but it is built on this assumption. And if you measure the power spectrum in different areas in the sky, you find actually that there is also a statistically significant difference in the power spectrum, both its shape and its amplitude. So this is the angular power spectrum of the CMB in different directions in the sky, in one direction and its antipodal direction on the sphere. And you see this discrepancy between the two hemispheres on the sky, and it's of order 20% effect on large scales, but it's observed at all angular scales. You can't see it by eye here, but on all angular scales, you see an excess of power in one direction in the sky relative to the other. And this is shown here. So this is just the amplitude of fluctuations in this map minus the expectation value from lambda CDM divided by the statistical uncertainty you expect as a function of position on the sky. And you see in the south sky, the amplitude that you measure from of these fluctuations that you measure relative to the expectation value is consistent with the standard cosmological model. But in the north sky, you see a 3 sigma discrepancy, and the data is statistically significantly higher in the fluctuation. So what you see is, even though you can't see this by eye, in the north sky, there's more structure in this area of the sky than this area, and it's around a 3 sigma high statistically significant result. And there are lots of other actual problems with the cosmic microwave background. I've actually run out of time, so I don't have time to tell you about them. I'm just going to say one thing, which is of interest because it was brought up earlier, and that is the assumption of statistical isotropy in the ALMs, the temperature fluctuations. Now, this is a plot of the angular correlation function of the CMB, which is just the Fourier transform of the angular power spectrum. So if you just take the sum over L modes and multiply by the Legendre polynomials, you get the angular correlation function. And this is the measurement that you get from Planck. These lines, these are all different maps, but they're all basically the same measurements, just using different cleaning processes. And this is the expectation value you get from lambda CDM. And you see that on large angular scales from 60 to 180 degrees, there's no power practically in the data. And that is, so that was thought that it just means that these CLs were low, but actually it suggests that there is a correlations between angular modes. It suggests that the angular modes on large scales are not independent, which is the assumption of statistical isotropy. Okay, so I'm going to stop here because I've run out of time, so sorry about that. But so this is the current state of affairs. So there's been a nice review that's actually headed by members of the CQUeST team, which I recommend you look at. And now there's many different dipoles that have been found in different data sets. And some of these you should take seriously, some of them you shouldn't. But the news seems to be that the universe does not seem to be exactly statistically isotropic in either the cosmic microwave background or the large scale structure. And that could present a very serious problem for the standard model of cosmology. So I'll stop there. So thank you.
Okay, thank you. So thanks for the very interesting introduction. So are there any questions or comments? Any question? Let me ask one question. So you said the velocity with respect to CMB and velocity with respect to the metal is different. How about the magnitude of the velocity? Magnitude is the same, only the direction different, or?
So D gives you a measure of the magnitude. So D is just the absolute value of the velocity. Mm-hmm. And then the actual direction of the dipole gives you the direction of the velocity. So the direction. So this tells you how discrepant the absolute value is.
I see.
And this gives you a discrepancy of the direction. Now.
So
yeah. Sorry.
So it's both magnitude and the direction is different, very different.
Yeah. Yeah.
I see.
Yeah.
Okay.
This area of the sky is very interesting because there's a lot of structure in the local universe in this regime, and actually the Milky Way is infalling into the large-scale structure of our local area, and actually the infall position is somewhere around here. So this whole region is a very complicated region of the sky. And that could be, well, I don't know. I don't know if that's related, but yeah. So there's a lot of uncertainty in this region of the sky anyway.
Okay. Are there any questions?